Okay, good afternoon. We're going to get started. Okay, so I'm Jim Halblin. I'm the instructor for aircraft detail design. And today we're going to have two teams presenting their small unmanned air systems. Yes, this is a small unmanned air system. It's got a 14-foot wingspan. So the first team is going to be Iluvatar. Excuse me, so I'm going to turn it over to Claire Colostro, their team leader, and she'll take it from here.
Thank you. So welcome to the final design review for Iluvatar Aerosystems. My name is Claire Colostro, and I'm the team lead. So here we have our team members: Mark Tversky, Paul Kim, Christine O'Keefe, Andrew Wilson, Joshua Parr, Peter Davidson, Joshua Day, Chris Sutphin, and Morgan Conklin. So here's an overview. We'll go over a design review, and then wind tunnel testing, which then helps drive the load predictions, and then which helped with our structural design as well as structural testing. So our STA, or our structural test article, was essentially the aircraft minus the nose cone, and then the landing gear, and then no empennage. So it was just strictly the wings and a fuselage. And we'll go more into detail on the structural testing later on in the presentation. And then turned into the FTA, or the flight test article, which then added on the empennage and then the gear. So here are design goals for the semester. This was driven by the statement of work provided by Professor Helbling. So we were to create this STA, like I mentioned. It'll be inverted, and then it'll be instrumented in the right wing with strain gauges and rosette strain gauges as well to calculate the strain in the aircraft with an 80% load of maximum loading. And then after our structural testing, it's not a requirement of the class, but flight test was a goal of ours, and we were actually able to achieve that, and we'll show you later in the slides. So here's a timeline. Like I mentioned, we did wind tunnel testing, load prediction, structural design, and then into manufacturing, which was just a little over a month, and that was a lot of work. And then we went into structural testing and then eventually flight test. So we'll go over our design review. So the design was originally proposed by Professor Helbling in the RFP, or request for proposal. And this was originally supposed to be a U.S. Department of Transportation surveillance aircraft. So here the payload up front would be a camera gimbal system with IR sensor to recognize and detect a license plate and a car in daytime. And then we had a design goal of being able to disassemble and then fit it into a 3-foot by 3-foot by 6-foot box. And that's why there's so many disassembly locations, and then to remain on station for 3 hours. So here's a preview. This is the Sting. This is what we named it. As you can see, it's a pusher prop, and then it is also completely electric based. And then we've got the camera up front, and we've got the inverted V-tail. As you can see in the drawings, we've got just under 15 feet is our wingspan, so it's quite a large aircraft. And then with the model here, we'll go to Mark Tversky, and he'll talk about the wind tunnel testing that helped predict weight.
Thanks, Claire. I'm going to talk to you about the wind tunnel testing. The purpose of the wind tunnel testing was to help the team improve the ability to predict the loads that the flight test article would experience in flight. So I'll be going over the model design, the test procedures, the data collection and reduction procedures, and then the results and conclusions we came to. So our model was constrained by the tunnel width to be 35 inches wide, and that brought our scaling factor to just over 5. This brought our mean aerodynamic core to 2.5 inches, and our planform area to 87 inches squared. So the plastic, the 3D printed plastic, isn't very strong by itself, so we made a steel substructure that runs throughout the wind tunnel model. We have steel spars and steel booms running through the model, as well as a steel centerpiece embedded in the fuselage to transfer the aerodynamic loads directly to the balance without loading the plastic. The wings were also pretty thin because of our thin airfoil profile, so we reinforced them with a uniaxial carbon strip on the top and the bottom to reduce their flexure. The landing gear was also detachable to test for how much drag the landing gear would actually cause. The wind tunnel model was tested at a running number of about 150,000, compared to $500,000 for the estimated for the production aircraft. We use a 6-degree of freedom balance, as well as a lab view acquisition code in the wind tunnel lab to test for the aerodynamic coefficients. Per Dr. Traub's recommendation, a realistic landing gear would cause 10% or less of the total drag of the aircraft. However, ours caused 12.9% of the total drag, and so it was removed for the remainder of testing. The lab view acquisition code used a coordinate system that was based around the front screw of the balance, and with a standard stability and control axis, with the x-axis going out the front, the y going out the right wing, and the z-axis pointing downwards. We conducted an angle of attack sweep from -4 to 14 degrees with the tail on and off, and a side slip angle sweep from -8 to 8 degrees with the tail on and off. The angle of attack was controlled with a stepper motor, but the side slip angle had to be set manually by turning a screw under the tunnel. Each angle of side slip was also tested at 0 and 6 degrees angle of attack to test for the stability derivatives. So our lift curve slope was slightly greater, as you can see, than our predictions. However, we achieved a similar maximum coefficient of lift and stall angle of attack. We ran into some problems testing for the drag because the data was erratic, and we attempted to retest, but the lack of wind tunnel availability prevented us from being able to retest. The drag was close to our predictions. However, the data compounded to make our lift and endurance parameters very erratic, and the data was unreliable for those. So in summary, our results show that our lift and drag were close to our predictions, as well as our stall angle of attack. However, our stability derivatives, endurance, and range parameters were not close to our predictions because the drag values were so erratic. The last stage of the wind tunnel testing was a flow visualization test conducted in UV light with tufts glued to or taped to the wings, fuselage, and tail. The tufts showed how the airflow moved around the sting during flight, or how it would move around the sting during flight. And it showed that the wings stalled at around 12 degrees, as the data predicted, and also that the tail did not stall at angles of attack as high as 18 degrees, indicating favorable stall characteristics, which would make it easier to fly. So in summary, the gear was removed for the test because it caused an unrealistically large amount of drag. The results were acceptable for our lift and pitch stability, and the drag results were usable but erratic, but these compounded and made our roll and yaw stability, as well as our range and endurance parameter data, unreliable. The flow visualization also showed that our stall would indeed occur around 12 degrees, and we had good flight handling characteristics. As I said before, the purpose of wind tunnel testing was to predict the loads, which leads us to load predictions by Paul Kim.
Thank you, Mark. So today I'll be talking about the VN diagrams and how the critical load condition was found. So today I'll be talking about the assumptions on how the maneuver load factors and the design speeds were calculated and how these were implemented into creating the maneuver diagram. Next, the gust speeds were calculated and to create the gust diagram, and as well it was adjusted for the gust speeds to create the final VN diagram, and our critical load condition was based off the final VN diagram. So our assumptions come from 14 CFR 23. This is the assumption for normal and commuter aircraft. Due to the lack of specifications for small unmanned aerial systems, we were able to use normal and commuter as best available specification. A key thing to note in this section is that the speeds will be talked about in knots equivalent airspeed. The maneuvering load factors, the limit load factor was defined in CFR as this equation. A key thing to note is that it was calculated to be 4.49 Gs. The RFP actually limits our limit load to be 2.5 Gs, and that's the one we use for the positive load factor. The 4.49 Gs was still used to calculate the negative load factor, which was negative 1.8 Gs. Design speed was also given by CFR 23, and the stall speed was calculated to be 21.8 knots equivalent airspeed. Using this value, we calculate the corner velocity, which is the minimum speed at max limit load factor, and that was calculated to be 34.5 knots equivalent airspeed. Moving on to design cruise speed, using this equation where Kc is 33 for non-acrobatic aircraft, the design cruise speed was calculated to be 46.0 knots equivalent airspeed, and then using this value, the dive speed was calculated to be 64.4 knots equivalent airspeed. Now that the four design speeds were calculated, these values were compared with the preliminary design results, as you can see in this table above, and the larger values were used as a conservative estimate for the initial flight envelope. As you can see, this is the maneuver diagram that was compiled. The stall speed, the corner velocity, the cruise speed and the dive speed were all plotted against this in the maneuver diagram. Now we had to calculate the gust lines using this equation. The gust speeds that resulted from this equation was unreasonably high due to our low wing loading. And so per Professor Hulbing's instructions, we forced the gust lines to intersect the cruise speed and dive speed with the limit load factor. And that was reverse calculated to find out what the actual speeds of the gust speeds were. As you can see in the designs, the gust lines, it's 8.51 feet per second and 6.08 feet per second. And in order to create the final VN diagram, this was adjusted for the gust lines, and this is the final VN diagram, and it was simplified to reduce clutter. And the critical condition was chosen at this top left for high agility in turns. And this was at corner velocity of 34.5 knots equivalent airspeed and 2.5 Gs. This is a summary of our critical load conditions that was defined in the VN diagram, which will be later used in the load predictions in the wing, empennage, and fuselage. I'll also be talking about the wing loads. So today I'll be talking about the types of loading, the strength approximation, the shear moment diagrams that the wing experienced, and the ultimate loads of spar loading as well. This is the axis system used. The origin of the axis is based on the leading edge and where the left wing and the right wing are predicted to meet. And X is aft of the centerline fuselage, Y is right outboard, and Z is vertical. These are the types of loads considered. Wing loading, which is calculated by the critical condition that I just mentioned in the previous section. Tail and load moment, which is the V-tail, transferring the load through the booms into the wing, which will be further discussed in Christie's empennage section. The span-wise lift distribution, which is calculated using strength approximation, and then the chord-wise lift distribution, span-wise drag distribution, and the factor of safety of 1.25 was implemented based on Professor Hulbing's instruction and industry standards. This is strength approximation, where it is the average of the elliptical and the planform distribution. 0 is where the center line of the fuselage is, and right here is 88 inches, which is the wingtip of the aircraft. The ultimate shear force in the Z occurred in the Z direction. There is a spike right here, and that is due to the concentrated force due to the boom transferring the loads into the wing, and so you see the spike there. The wing station is at 3.53, and the wing station is the connection of the wing to the fuselage right here. And so using that point, we were able to calculate the corresponding maximum, or ultimate shear force, and that calculated to be 59 pounds. Similarly, the ultimate bending moment occurred in the x-axis, and again, using the same wing station at 3.53, the ultimate bending moment was 1780 inch-pounds. This is the list of the ultimate loads that were calculated in multiple axes. Again, the bolded values are the ultimates that I just explained in the previous plots, and these were used to further in Josh Parr's wing sizing section. The core distribution, the CP total, which is the green line above, is the sum of the upper surface and the bottom surface. And using the CP total, we were able to integrate and find the center of pressure, which is at 0.33. And so using this value, we were able to determine the percentage of load carried by the forward and aft bar, which is 85% and 15% respectively. In summary, these are the ultimate shear force and bending moments that I just explained, and the spar loads of 85% on the forward spar and 15% on the aft spar. And next I'll hand it off to Christine O'Keefe to talk about the empennage loads.
Thank you, Paul. So for the empennage loads, I will be going over the wind tunnel data, the actual versus selected airfoil, the CL comparison, the lift distribution, and the shear moment diagrams. So as Mark mentioned in the wind tunnel data, the moment diagram, as you see here, is very erratic, so we were unable to use it. So we used the critical condition described in the VN diagram, which is 65.2 feet per second, which is equivalent to the 34.5 knots equivalent airspeed. Here's the coordinate system that was used to determine the loads that are acting on the empennage. And here is the force projection. Because we were at an angle, we had to find the force normal to the surface. So originally we chose a NACA 0012 airfoil. However, because of the angle of our empennage, it actually is projected to be a little bit wider, as you can see by the red outline here. And in comparison, we compared it to the NACA 0018, which had similar data for the 2D, and we were able to use that for the shrinks approximation. So for the shrinks approximation, we made a few assumptions which gave us a conservative analysis. This includes a cantilever beam and no support from the tail booms. Here's the lift distribution that was determined from the shrinks approximation as described by Paul Kim in the wing loading section. Here's the shear loading, and you can see at the wing station we have -7 pounds. And here's the moment loading, which is at 5 foot-pounds up here. So here's the summary of all the loading that will be acting on the empennage and will be used with Josh Parr's empennage sizing section later on. Then we can move on to the fuselage loading. This is based off the critical load condition and the shear moment diagrams. For the critical flight condition, we actually use the 2.5 Gs that was used in the VN diagram described by Paul Kim. And then we also calculated nose gear and landing gear and main gear conditions. However, we weren't analyzing those because the critical flight condition was more of a concern for us. And these were based on 2.5 for the flight condition with a factor of safety of 1.25, and then 2.67 Gs for the nose and main using CFR 23. So for the diagrams that I'm about to show you, the steps on the shear diagram are based on the internal components or the anticipated positions, and the slope is also due to these internal components along with the tail moment. So here's the shear diagram for the fuselage. This is the ultimate shear load. As you can see here, this is based on the tail loading and the steps are shown. The 3.13 Gs is based on the 2.5 Gs multiplied by a factor of safety. And here is the moment diagram. Again, this large moment here is based on the ultimate bending moment based on the tail acting on the forward spar. So in summary, the max shear and max moment for the flight condition are what are going to be used for the fuselage sizing later on in Joshua Parr's section. And that can be seen here for the 290 and at -1,802 inch-pounds. So as I mentioned before, there's a concentrated tail load, and that's going to create the most moment acting on the fuselage. And these ultimate loads will be used for sizing by Joshua Parr. After the loads were calculated, we actually moved on to materials to determine the material properties that will also be used for the sizing, and I will hand it off to Andrew Wilson to describe the material testing.
I'll be talking about the material testing. The reason why we material tested was to get the material properties which will be later used by Peter Davidson in the ANSYS analysis section. Also, we wanted to verify that the materials we selected would withstand the loads as discussed by Paul Kim and Christine O'Keefe. As an overview, I'll be talking about the testing procedures, the tensile test results, the shear test results, the cantilevered foam beam results, and environmental impact of the materials we selected. We had 6 E-glass specimens in quasi-isotropic layup, and the reason why we chose a quasi-isotropic layup is because ANSYS analysis requires an isotropic material. So the material properties we gathered were from quasi-isotropic materials. 3 of those tensile specimens had strain gauges attached to them so we could find Poisson's ratio. We also had 6 carbon fiber tensile specimens, and 3 of those also had strain gauges attached to them. The shear and beam specimens, we had 4 E-glass shear specimens, and this was also in a quasi-isotropic layup. And we also had 4 carbon fiber shear test specimens. And we also had 1 sandwich material of each carbon fiber and E-glass. And the sandwich material is 2 plies of the composite and then a foam core on either side. And we also had 2 cantilevered foam beams. The tensile test specimens, the ones without strain gauges were tested until failure, and this was to find the ultimate strength. In the specimens with strain gauges, as shown here, we have a lateral strain gauge and a longitudinal strain gauge, and that ratio will give you Poisson's ratio. And those were tested to find Poisson's ratio. The shear specimens were tested in a 3-rail test apparatus system, and both the shear and the sandwich specimens were tested until failure. And we had an issue with some of the shear tests because As you can see here, the aluminum doublers that we used to ensure that they would fail at shear, those actually delaminated, and you can see a lot of bearing failure here. And so we actually had to retest and change our methods a little bit, and we actually got much better results, as you can see here. The cantilevered foam beams, we had a beam, as you can see here, fixed at one end, and a load was applied to the tip, and a linear potentiometer measured the tip deflection, which was used to find Young's modulus. These are the equations we used to find the equations of the tensile test, shear test, and the cantilever beam test, respectively. So, as you can see here, the tensile test, our sigma ultimate, is the force applied over the area, and Young's modulus is the slope of the stress strain. In the shear test, the key thing to note is that the area is actually a cross-sectional area, it's H times T. These are the carbon fiber tensile test results. As you can see here, we got a sigma ultimate of 70.6 KSI. In this section here, the slope gives us Young's modulus, and this section is where we took off the extensometer, so that's why it's vertical. These are the E-glass tensile test results, and we had a sigma ultimate of 28.5 KSI. We had a Poisson's ratio of carbon of 0.34 and a Poisson's ratio of the E-glass of 0.32, and a Young's modulus of 61.6 MSI and 11.3 MSI, respectively. The carbon fiber shear test results, these actually vary a little bit between specimens, and this could be because multiple people were included in the manufacturing process of this, so each person has a different method of manufacturing, and so that could determine the results of the variance. These are the E-glass shear test results. This is actually one of the specimens that failed in bearing, as you can tell by the peaks and valleys. So it would tear through, and it would have gained some strength and then tear through again. These are the sandwich shear test results, and these definitely failed in bearing mode, as you can see here. And because they failed primarily in bearing mode, these results will not be used. And here's the shear test results table. The average for the carbon fiber was 27.8 KSI, and the average for E-glass was 21.58 KSI. And even though we did not use the results for the sandwich specimens, the results are here at 799 PSI for carbon fiber and 816 for E-glass. The cantilevered foam beam test results granted a Young's modulus of 3.69 PSI. And environmental impact, although the materials we selected were not inherently dangerous, there are some precautions when handling them, and this includes wearing goggles, gloves, and other protective equipment that makes you less itchy. And these materials can be disposed of according to local regulations. This is a summary of our material testing results, and these properties will later be used by Peter Davidson in the ANSYS analysis, and also by Joshua Barr in the structural design.
Thanks, Andy. So I'll start first with wing configuration and sizing. As you can see, there's our wing here, and then this is more of the internal structure for our wing, which you can see right here. It's important to know that we actually show the wing box ribs, although it's actually part of the fuselage. It's really important for the wing structure to transfer the load from the wing to the fuselage. And I'll be covering briefly the wing parameters, the spar spacing and sizing, which you can't see because it's internal, the rib locations, and the rib spacing and sizing. So to start off, we have this massive wing here that's 14.7 feet. We use an Epler E67 airfoil, which is actually relatively thin airfoil. Then we have a root chord of 1.39 feet, and you couple that with a taper ratio of 0.5, you get a tip chord of 0.7. So you have this long wing, small tip chord, small aileron. We have to use thin spars, and that'll come into play later. So as you can see here, we have our spar spacing shown up on the screen. The distance from the forward chord, or from the tip to the forward spar is 17% chord. The distance from the leading edge to the aft spar was 60% chord, and this is at the tip profile. And then also the distance between the center line of the aft spar and the leading edge of the aileron is 10.5%. So with the spar sizing, we use this equation to find the required moment of inertia. Then we plug that required moment of inertia into this thickness equation to find the required wall thickness. So as you can see on there, our D0, or D initials, are our initial outer diameters. and the DIs are the initial inner diameters, and that was based off the thicknesses. And I'll talk more about that in just a second. And then as you can see here, this is our rib spacing. This is important to note that you can see the tail boom, and with our tail boom, we have a rib on either side. And then with our just two assembly locations, which are needed to meet our transportation requirement of fitting in that 3 by 3 by 6 foot box, we have a rib on either side of that, and then we have a rib on either side of the aileron to close those, and we have our projected hinge rib, and then we have our wingtip rib, and then we also have our fuselage attachment rib. Then this equation was used here to find the thickness for the ribs. H is the root rib height at the F spar, since that was our thinner spar. Then the required thickness was found to be 0.01 inches. And we decided we're going to use 2-ply carbon fiber because that was our minimal structural component that we're going to use, and so that was our bare minimum. And that comes out to be 0.025 inches. Now, as you can see here, this is a summary of all of our parameters. It's important to note that these are the original dimensions, but when we went to our supplier, which was Clearwater Composites, we weren't able to get these exact dimensions, and so the closest dimensions are shown here. This is what we actually use for the forward spar and the aft spar, and then our rib thickness did bump up to 0.025 because that is 2 layers of carbon fiber. Moving on to empennage configuration and sizing. We're going to cover the empennage design, the internal structure configuration, the empennage boom connection, the empennage spar joint, and the spar boom connection. The empennage design has a half span of 1.58 feet and a chord of 1.05 feet. It's using the same 2-ply thickness of carbon fiber, which is 0.025 inches. You can see the internal structure shown here. It has this is just a half span of the V-tail. On each side of the V-tail, there are 5 ribs and then a carbon fiber spar. The empennage boom configuration, we actually had an E-glass layup, which is plus minus 45 degrees symmetric layup, so there's 2 plies on either side of the boom to connect the boom to the V-tail, and that was mainly just to strengthen that point and make sure that the V-tail did not slip out of the booms. Then for the empennage spar joint, we use a PVC L joint that was just epoxied into the 2 carbon fiber spars. This allowed for more continuous flow of the forces throughout the tail. We use PVC because it's lightweight, inexpensive, readily available, and is plenty strong because the tail won't see a lot of load. Then we have the boom spar joint. For the boom spar joint, we just drilled a hole into the boom, inserted the spar in there, and epoxied it into place. And then once again, we did an overlay to strengthen that joint. This is our final configuration shown here, or you can just see it on the actual model right there. Going on to spar sizing, we had an initial outer diameter that was assumed to be 80% of the airfoil thickness. But this is back in prelim, that was 0.864. And then we had a required moment of inertia that's shown on the screen and was found using this equation. Then we used the required thickness equation to find our required thickness, which is also shown up there. The final outer diameter and inner diameter was reselected to be 0.860 inches and 0.750 inches based off, once again, our supplier limitations. Then we have our empennage rib thickness, which has a required thickness found using this equation shown on the screen. Then you have thickness required was 0.003 inches. And this is increased, once again, to 2 layers of carbon fiber, because that was our minimum that we're going to do for any component. That was 0.025 inches, so we were plenty thick on that. Then moving on to our booms, we had initial outer diameter that was assumed to be 1 inch in prelim. Then you can see our required moment of inertia is found using the equation above, and the value is shown. But then the required thickness is also found using that equation and had that resulting value. It was important to note that we bumped out that thickness a lot because it's incredibly small, and you can't get a carbon fiber tube with that kind of thickness. So we went with the final outer diameter of the 1 inch that we initially predicted because our supplier had that. But then the matching inner diameter was 0.938 inches. Here's a brief summary of all of our parameters. You can once again see our estimates, and then you can actually see what we actually use based on the supply that's available to us from our supplier. Moving on to fuselage configuration and sizing, I'm going to cover the fuselage dimensions, the longeron sizing, bulkhead sizing, and then a summary of the components. So the bulkhead thickness is 1.05. We have a bulkhead outer diameter of 11 inches, or 2.8 inches, my bad, and a bulkhead inner diameter of 8.73 inches. We also had a 1/8 inch firewall, and thick that was that big, and it was plywood. We have a rib thickness of 0.025 and a skin thickness of 0.025. Both of those were 2 layers of carbon fiber at a plus minus 45 degrees symmetric layup. And the overall fuselage diameter is 11 inches. As you can hear, this is a brief image of one of our bulkheads. I was mainly shown to show you some of the values you're going to see in the equations that are going to follow. You have H, which is the height of the bulkhead section, and then you have C, which is the distance to the neutral axis. The neutral axis shown, and the width of the longeron, which is the variable W. Using those variables, we were going to calculate, you're going to see them come up in several equations, like the ones on the screen. We had an e-glass and foam sandwich for the longerons. So it looks just like this. However, we used e-glass on either side, and there's just 2 layers on each side with a 1-inch thick piece of foam in the center. The ultimate bending moment that we predicted to have to withstand is 1,802 inch-pounds. Then you can see the required moment of inertia equation. We put the required moment of inertia into the required thickness equation to get a required thickness that's shown on the screen. Now that's incredibly small, and so we end up using 4-ply e-glass, which has an overall thickness of 0.1 inch. So we're plenty strong in that area. Then we have our bulkhead sizing, which is designed to provide shear strength. It had an e-glass and foam sandwich. The equation for that required thickness is also shown on screen. Ultimate shear force needed to be predicted was 290. That's from the Venn diagram which Paul presented. Then you have our thickness required was once again incredibly small, so we will use just a 4-ply e-glass layup with 2 plies on e-glass on either side of that foam. And that gives us a total thickness of 0.1 inch. You see our firewall size is just that 1/8 inch plywood, and that's a 6.2 inch diameter, which is determined by the fuselage diameter at that location. Then you have our floor ramp and ceiling. All of these are 4 plies of plus minus 45, 0, and 90 symmetric layup, and that comes out to a total thickness of 0.1 inch. In summary, we have our longerons, which are 4-ply e-glass with a 0.5 inch foam sandwich in the middle. Then you have our bulkheads, which are 2 plies of e-glass on a 1 inch foam piece with 2 plies on either side of that 1 inch foam. They have our floor ramp and ceiling, which are 4 plies of e-glass. For more information, you can see this big, long 49-page drawing package for more exact details if you want. Okay, now I'm going to pass it off for fast display analysis to Davidson. All the configuration and size I used all went into his ANSYS evaluations.
Thanks, Josh Parr. So for the fastening joint analysis, as an overview, the fastening joint analysis is calculated for the critical loads that the main gear and nose gear would experience, as well as calculating the thickness for aluminum doublers that we put on the floor, as well as top of the main gears, in order to reinforce the floor connections. So this was the equation that we used to calculate the critical load. Here, the n is the number of bolts. So for the nose gear, that was n equals 1, and for the main gear, it's n equals 2, because there's 2 separate bolts. It was also had a factor of safety of 1.25 built in, and this was considered to be a conservative estimation for the horizontal load, because this 100 pounds force, the critical load, was treated to be applied vertically to the gear on a single gear, and since it's vertical, that's considered a conservative estimation for any force that is also horizontal applied to the gear as well. So for the nose gear, the scenario was a hard landing on the nose gear, and we wanted there was 1 bolt, 1 axle, and we had doublers on both sides of the e-glass floor inside the nose gear. So the fastener sizing for the nose gear connection was calculated to be 0.0558 inches, as seen in the equation above, and that correlates with standard bolt size, near standard bolt size of 0.187 inches. And then the load was reevaluated, the critical load reevaluated for that bolt size, and that was 1,130 pounds. For the failure modes for the nose gear, you have the shear failure, bearing failure, and shear out failure. You can see the equations used for them. See the cross-sectional area for the shear failure was the cross-sectional area of the bolt, and for the shear out, it was the thickness of the doubler times the distance from the doubler itself to where the force is being applied. So those are our failure mode calculations right there. The main landing gear is 2 axles, the same size as the nose gear for the connection to the wheels. So the same equation was used for that, but there's 2 bolts attaching into the glass floor, so n equals 2 for those bolts. And the force applied to this was also 100 pounds, and it was applied to a single wheel. So it would be a 100-pound vertical force applied to a single wheel, straight up like that. So these were the main landing gear loads as calculated using the same equations as before. So you see 6,796 is calculated via the critical load. That's pounds. So for the diameter for the bolt, it's calculated 0.459 inches and correlates to standard bolt size of 0.5 inches, and reevaluated for that bolt size, the force of failure was 617 pounds. So for the aluminum doubler sizing, this is a photo of the aluminum doubler used for structural testing, to give you an idea what the aluminum doublers look like. For the nose gear, it's calculated to be a thickness of 0.0625 inches, and for the main gear, it's calculated to be 0.125 inches. So in summary, these are the sizes of the bolts we're using for the fasteners for the gear, nose gear, and the main gear. Next up, I will discuss the ANSYS analysis of the wing that was used in the structural test article. So as an overview, I'll talk about the ANSYS procedures, the model setup, the load constraints, and the ANSYS results, the spar stresses, skin stresses, rib stresses, and the displacement. The reason why the ANSYS analysis was important is because it allows our ability to predict loads in the wing. It was used later, will be used later on when compared to the structural test article compared to strains, and it's also used to feed in the ultimate loads that calculate the margin of safety, predicted margin of safety of the flight test article. So the ANSYS is a model of the left wing of the aircraft, that wing, and it evaluates the ultimate load factor and also evaluates strain for comparison to the structural test results. So this is how the model was set up. It was set up with 8 remote forces applied along the forward spar that simulates the wing load. Next slide, I'll discuss about how these loads were calculated. It also has the tail boom is included in the model to calculate the moment and the force that the tail would apply to the wing as well. So this is our inboard rib right here going all the way out to the outboard rib. This rib right here is considered to be the rib that's next to the fuselage, and that is considered to be the fixed point of the wing. In addition, the 2 spars have a symmetrical constraint to simulate the connection to the spars to the other half of the wing model. And then there's 8 remote forces, and you can see 2 spars, the ribs. In addition, the ANSYS model also included the foam in between all the ribs as well as the skin. And also, breakaway connections were modeled by creating a slight gap in the spars and adding the correct size ferrule diameter, which we'll discuss later, in between the breakaway connections. So first breakaway connection here and second breakaway connection here. So this is how the remote forces were calculated. It was derived from strengths approximation. Strengths approximation was divided into 8 points that were equally spaced out. And then these points were calculated that had basically numerical integration about them so to evaluate an equivalent load. So you can see the X location from the root to the tip, as well as the load associated with that point. And then there on the right, you can see strengths approximation with the graph of the forces, the location of the forces applied there to give you an idea of how the wing was loaded. So this is the meshing of the model. The mesh was set up so that the runtime of ANSYS would take between 2 and 5 minutes, depending on the computer. And there's the mesh of the skin. And these are the material data that was used in the model. These came from Andy Wilson's materials testing section, except for the carbon tubes that came from the manufacturer specification page from Clearwater Composites. So the results for the stresses in the spars, 4,700 psi in tension, 6,500 psi in compression in the forward spar, and similar in the aft. And see, this is the stress distribution. Our most highly loaded location was right here, right next to the wing root, although the forward spar was also predicted to be highly loaded, highly stressed in the middle of it right there too. For the tail boom, it's predicted to have 6,600 psi in tension, 7,000 psi in compression. And that, you see, happens right next to where it connects to the wing, which to the tail boom is basically a fixed point, so that is expected. For the foam, all principal stresses were within 5 psi, which is expected because the foam is just there as leftover manufacturing, and also the transfer loads from one rib to the other, so it is very, very lightly loaded. For the skin, we evaluate the shear stress in the plane of the skin. That is found to be about 1,000 psi as the maximum value, and that occurred near the wing root connection. For the rib, the shear stress was evaluated with the rib in the vertical plane, so the plane along the side of the rib, and that's found to be about 2,200 psi is the maximum shear. So you can see the shear in the vertical plane, and the shear was concentrated around the spark connection holes. The location of the critical rib was the 6th rib that's located right next to the outboard connection point. This result is dubious, however, because the shear predicted, we expected it to be over here, and all these ribs were also highly loaded in shear. The maximum values were on this rib. For the displacement, there was 1.4 inches of displacement on the wingtip and 1.9 inches on the tail boom. This result was also dubious because we expected a lot more displacement, and as you will see in the structural testing section provided by Chris, that there will be more displacement, and there are several reasons that this could happen, one of them being the material for the wing was treated as isotropic, even though two-ply carbon fiber is not isotropic. The fasten joints, or the joints connection between wings weren't modeled correctly in ANSYS, as well as having just incorrect material values are all potential reasons, and that will be discussed further in detail later on. So as a summary, these are the stresses experienced in the wing structural test model in ANSYS. And next I'll discuss the margins of safety, which were used from the ultimate loads that were applied to the ANSYS model. So as a review, I'll go over the margin of safety calculations, interpretations, and then the margins of safety for the actual test article. So this is the equation used to calculate the margin of safety. And ultimate loads had a factor of 1.25 applied to them, and that's the ultimate stress, and a factor of safety of 1.25 applied to them. So a partial margin of safety is required to proceed, and the desired margin of safety is greater than 0.1. Now, large margin of safety just means the component is over-designed for the amount of stress that it's experiencing. So using the ultimate loads predicted, as well as the allowable material results, these are the margins of safety. As you can see, they are very high, with the lowest value being 1.57, which is much greater than 0.1. So all of our margins of safety are positive. So stress-wise, that means they're over-designed. However, a large component of using the high aspect ratio of our wing, which is required to meet the endurance requirement, is that deflection is a huge issue. So and that deflection is driven by stiffness. So designing to stiffness, these margins of safety are only for stress, not stiffness, which is why the margins of safety are so large, because the wing should be designed for stiffness, not necessarily just for strength. So with these margins of safety established, we're now able to proceed into the structural test article manufacturing, which Joshua did, and I'll talk about.
Thank you, Pete. So first I'll go over the STA manufacturing, our structural test article, and first the wing manufacturing of the STA. So for an overview, we'll go over the rib manufacturing as well as the foam core, instrumentation, and the final assembly and skin application for the wing. The wing dimensions are as shown, and for all dimensions in manufacturing, we use this Seadrill A006 drawing package in order to design off of and manufacture. And here's an image of the wing, which the ribs and spar shown, as well as the boom attachment. To make the ribs, we created a full sheet of 2-ply carbon fiber and then created aluminum templates in the rib shape and cut those using the bandsaw and sanded them down to the correct airfoil shape, and then we drew those outlines on the carbon fiber that we had made and cut that out using a bandsaw, and then sanded those down to match the aluminum templates that we had also made. The foam core we created by layering 3 layers of the foam on top of each other, and then we attached our aluminum templates and used this cutting jig here in order to drill the spar holes through the foam, and we did that by serrating the edges of the aluminum and then attaching an electric drill and drilling through the foam. We then hot wired those sections using 2 people, and we would cut in small sections and time so that we would get a decent airfoil shape. To instrument our wing section, we instrumented this right wing up at this section, which was the originally calculated location of the most stress. We put 3 strain gauges on the top and bottom of both the forward and aft spar, as well as 3 rosette strain gauges, as shown here. And then those strain gauges were attached to a DAC, or data acquisition system, that was used to record the data from our structural testing. To apply the skin and assemble the wings, we laid out the wing sections and put the ribs between each section, as well as the spars through the wing sections. And as you see, there were 5 wing sections. We needed that many sections in order to both be able to put a plus minus 45 degree carbon fiber over the wing sections, as well as be able to disassemble it so that it will fit in a 3 foot by 3 foot by 6 foot box. We then applied the carbon fiber in a 2-ply layup over the wings and vacuum bagged that. As you can see, we allowed extra along the trailing edge so that we could cut up to the trailing edge and have a good trailing edge for our wings, as well as we smoothed out the leading edge of the wings so as not to disturb the airflow over the leading edge. The wings are attached using ferrules within our spars. We epoxied those ferrules in, and as shown here, so that one wing spar can slide over the other wing section, and so we can attach our entire wings. The fuselage was manufactured by creating the bulkheads, the longerons, the firewall, the floor ramp, and ceiling, and then applying the internal components and the skin. Here are the fuselage dimensions that we used, and you can see here the bulkheads within our fuselage, as well as the wing sections that were attached to our fuselage and the ceiling that is inside of our nose cone. To make the bulkheads, we created foam sections and cut those out using a hot wire, and then we created a large sheet of 2-ply e-glass and cut the bulkhead shapes as well as the longeron shapes from that using the water jet cutter. And then we epoxied those onto the foam, and we sanded down the e-glass and the foam in order to make them all fit together nicely. We then epoxied the longerons onto the bulkheads at their correct locations to make the fuselage shape. The firewall was originally designed to be 1/8" plywood. It's within this section, it's a little hard to see. But due to availability, we used, in the machine shop, we used a 1/4" plywood, which would just be slightly over-designed. And then the firewall was attached to the fuselage using epoxy onto the longeron sections and the ramp. And the motor was attached. The internal components of the floor was epoxied onto the bottom flat section of the bulkheads, and then flanges were used along this front edge as well as along 3 bulkheads in order to help with the impact from landing so that the floor would not come up off of the bulkheads. The center wing was attached by drilling a hole through the fuselage skin and going through the internal fuselage ribs, and the boom would be slid in and then the wings were attached. To make our fuselage skin, we created a foam mold and cut that using the hot wire, and then sanded it down and to make it as close to a perfect circle as we could. We also used the aluminum templates in order to help us cut that. And then we put a layer of quick release film over the mold and a 2-ply e-glass plus minus 45 degrees skin over that, and vacuum bagged that layup. And then to remove it, we made one single cut because it was flexible enough to be able to then wrap it around our bulkheads and reattach it that way. So the final assembly, we wrapped the skin, like I said, around our bulkheads and applied a 2-ply overlay. We put duct tape along the outer edges so that it wouldn't come up during the time it took for the center section to dry, and then we removed that duct tape to finish the overlay. The wing box was then attached, and as you can see here, in order to provide extra support, we did an overlay across the top of our STA as well as across the bottom, so to help reduce the amount of flexure in the wing section. So the STA was then assembled, go over the full wing assembly and the full assembly of the structural test article. To attach the wings, we drilled holes from the top of the wing through the spars and ferrules and out through the bottom of the wing, and then attach that using clevis and pins so that it would not fall off during testing or flight. We also created access panels on the side of our fuselage so that we would be able to access the internal components of our aircraft and place the electrical components inside. And those were reattached using Velcro so that we could keep the skin and not cause drag. And now Christopher Sutton will discuss the structural testing.
Thank you, Josh. So I'll be going over the purpose of structural testing, our STA setup for testing, our data collection, our load applications, our axial and shear strain gauge installation, and our comparison to our ANSYS results. The purpose of this was basically to collect data to compare to our ANSYS results. The main thing we were looking for was deflection because we were worried about the wing being overly flexible, which is what we found out it actually was. So here's our setup. We can see the STA here in this nice foam mold, which was used both to prevent rotation of the aircraft during testing and to keep the wings from contacting the table when the load was applied. You'll notice that there is no nose cone on here yet. That is because we installed the nose cone later to allow for access during manufacturing. Also, we used ratchet straps to keep the fuselage from rotating. So load applications locations, where we had a total of 8 load locations. We've had 5 load steps, which equate to a total of 30 pounds. We applied this load to each wing to keep the aircraft balanced. And we instrumented only the right wing because we only have enough data acquisition systems for one wing worth of instrumentation. So here's our load application steps. You can see it goes to 80%. That is 80% of the limit load, which is what was required in the statement of work. In this column, you see the locations that loads were applied, and you see the cumulative weights at each load location. So our axial strain gauges were installed 4 inches from the disconnecting first detachment location. That's because the ferrule ends about 3 inches from that location, and we didn't want to have any interference. Further, the rosettes were actually installed on this rib. The section, we have 2 ribs that are spaced about 1 inch apart. These 2 is where the boom attaches for reference. So our rosettes were installed so that we have 1 gauge going along this axis, 1 gauge going along this axis, and then 1 gauge going 45-degree angle between those. We have 3 strain rosettes. Right now, the top of the wing is at the bottom of the image. This is because we installed it, the way we tested was the fuselage was upside down, and so we had this image taken as the wing would be installed. So for our data collection, we installed 12 axial gauges. We had 3 on top and 3 on bottom of each spar. Of these, only 9 actually gave us data into the data acquisition system, and of those, only 6 of the gauges actually gave us usable data. We had a similar issue with the strain rosettes. We had 3 strain rosettes. 2 of them actually had all their gauges working, and of those, only 1 had all the gauges actually giving usable data. So you can see all strain data. You notice these are the 3 gauges that were giving us erratic data. When we eliminate those, we have our nice linear curve, just like we'd expect. And then moving on to the shear strain, we used this equation and this orientation for our rosettes to calculate our shear strain. Here we see with both working rosettes, you see again, this one's giving very erratic data. When we remove that, we have data that also looks erratic, but this is mostly due to the low loading. It is almost certainly just noise causing that variation. So I'll compare this to the ANSYS results, which is the main purpose of this testing. So to start with this, we have at the top of the forward spar, with the orange for all these graphs that I'll be showing is the ANSYS result, and the blue is our result. For the top of the forward spar, we have our result is about twice the magnitude of the ANSYS result. We move to the bottom of the forward spar, it's about 1.5, 1.6 times. So they're quite a ways off as far as shears look, as far as the strain is concerned. But it's still within an order of magnitude, so we were confident at this point we still test. We weren't worried about anything breaking. The loading is still low enough that it's not a huge concern as far as strength. Again, with the top half spar, you can see it actually goes to or change about 4 times, and this is also reflected with the bottom half spar. So all our values of this are significantly different from our ANSYS, but as Peter Davidson described his ANSYS section, we found that there were issues with the way the ANSYS was being run, and when it was rerun, we got answers that were more similar, but we had to use enough assumptions there we're not comfortable actually presenting that data. So here with our screen, again, we see our data is erratic, compared to low loading on the ANSYS, but again, this is so low loading on these gauges that it's unlikely that we could get any less noise in there, because I've noticed while testing that if someone opens a door or walks by, you'll see the gauges actually changing because that's so lowly loaded. So for our deflection, we have, our actual measured deflection was 14 inches. Our predicted was 1.4 inches, so it's off by a factor of 10. This means that we weren't really able to accurately predict our results using ANSYS, but it was still within bounds that we considered acceptable to fly. If we were to refly, we would strengthen and stiffen the spars by adding in wooden dowels or other spars inside of those spars to prevent deflection. So in summary, we had excessive deflection, which was the main issue why we were not able to accurately represent our data, our results. From our 6 usable strain gauges, we had a critical loading of about 2,100 microstrain axial, and for our 1 usable strain rosette, we have about 240 microstrain in shear. Our measured strain values for axial shear loading were again higher than predicted. It's likely due to a mixture of the CATIA modeling and the ANSYS modeling, being slightly inaccurate in a couple of very small areas that have very large impacts in the result. Now I'll hand us back to Joshua Day for the manufacturing of the FTA.
Thank you, Chris. The FTA was assembled from the STA, as we previously discussed, by attaching the nose cone, the landing gear, and the empennage. The landing gear was manufactured. The nose gear, as shown here, was originally designed as such. We ended up changing the design just slightly by adding a flange along this bottom section to make it easier to apply an axle for the wheel. To make the nose gear, we created a foam mold and applied 4 plies of carbon fiber along the top section, and then 8 full plies, and then 4 more smaller plies to reinforce this top section where it would be connected to the actual flight test article. Now, to connect it to the article, we used a 1/2-inch bolt and then bolted it on both the top and bottom of the gear, as well as the top and bottom of the floor inside of the fuselage. The main gear was designed as shown, with it being a 32 ply, and as you can see, we used E-glass flanges along the floor on both the top and bottom to reinforce this section where the main gear would be attached. The control surfaces were manufactured by taking a bandsaw to these outer edges up to the locations that we wanted, and then using a Dremel to go along this section, and then we carved out the foam inside of that section to allow it to be bent. We also cut some slots in along the top upper surface to allow the deflection or the servo to deflect the control surface easier. The servo attachments were created by, again, dremeling out the skin and taking out the foam, and then hot gluing the servo into that location. The tape there is just to keep the wires inside so that they wouldn't get damaged. And then we also did the same for the empennage control surfaces. The boom was attached, and it needed to be detachable so that it would fit within the 3-foot by 3-foot by 6-foot box. So in order to make that happen, we had to sand down the attachment locations so that they would fit within the boom sections, and then we drilled from the top of the boom down through the handmade sanded section out the bottom of the boom and used pins in order to attach it. The servo, as I mentioned earlier, were attached. As such, the servo to control the nose gear is shown here, and we created a aluminum plate and drilled holes in it to attach the servo and allow the nose gear to be able to be rotated for control on takeoff and landing. The control surface servo wiring is shown, and we ran the wires from the servos through the spars and then into the fuselage, and we were able to connect it that way. We also had disassemble locations and quick releases, which didn't always function correctly. But we also had our servo run from the empennage down through the boom, and then it ran along the bottom section of the wing here, and then into the fuselage skin and into the fuselage. The electronic components that we used were a Phoenix Edge 80 HV ESC, as well as 2 LiPo batteries, one 7-cell and one 6-cell, totaling about 13 cells of LiPo batteries. And we also had a GoPro camera that we put on the front so that we could record our flight, 5 servos, and an Eternity AeroDrive 5K motor. To make our nose cone, we created a foam mold and then put a 2-ply e-glass over that. And then we carved out a section of the skin and the foam in order to put the camera mount inside. The camera mount is 3D printed and it detaches. Here's one of our older ones that we used during flight test, and it detaches, and there's a pin location so that it won't come out during flight. So the final specifications of our aircraft, we had a wingspan of 14.83 feet, length of 7.5 feet, or 7 feet 5 inches, and it weighed approximately 35 pounds, which is slightly over the 30-pound weight limit that we wanted. And we actually had a weight distribution of about 85% on the main gear and 15% on the nose gear. Here's our final assembly of our aircraft and a second photo. And now Maureen Conklin will discuss the flight test.
For flight test, I'll be going over our test objectives, the overview and background of our test flight, the procedures we use, and results and conclusion from our test. Like Clarence said before, flight test was not required for the statement of work. However, we set it as our goal to meet, and we were able to do that this semester. For the objectives, we split it into ground and flight. So we went to do it in range, a static engine test, and high and low speed taxi. And that would be followed by a flight test if the ground test was successful. And then we did takeoff, maneuvering, and stability, as well as landing, which most people would say is a requirement after takeoff. For the overview of background, we did our taxi testing on the campus RC field, which is a dirt runway. And then we did our flight testing at the CVMA airfield, which is an improved runway. Our test pilot was Michael Rosnick, and we followed all the rules laid out by the FAA, the AMA, and the CVMA. For procedures, we did the FTA assembly as Joshua Day previously discussed. However, we didn't time it for the RFP. We were having some issues with the servo wires and the wings. For in-range, we used the controller to ensure that we had communication with the FTA throughout flight. And then we did the CG verification by using the weight on wheels and statics. And then we did the control service. So we moved the control services in a specified range from the test plan, and we ensured that they all received power, and we're doing the correct control inputs. For the static engine test, we increased the throttle to 100%, so we can verify that it was receiving and maintaining power. For our taxi, for the low-speed taxi, we aligned with the center line of the runway and accelerated to 20% power. And we tried to maintain directional control as well as the runway, but we didn't have a center line on here. And we had a sensitive nose wheel, so we fixed that for flight test. For the high-speed taxi, we did the same thing, but at 80%. For the actual flight, we did the same thing, in range and CG verification, and then we did the takeoff downhill. After we started uphill, but we weren't getting enough power to rotate, so we tried downhill. We do a slightly aft CG. It was actually right next to the main. And then for stability, we didn't have any sensors on board. We could kind of see the tendencies and the input from the pilot. For maneuvering, we had low and high bank turns, which we were able to see, but again, we didn't have sensors. And at one point, we think we had a 60+ degree bank, which is inching up in our flight envelope. And then, of course, landing. We did have a successful takeoff. However, we lost our left main after we rotated, so it caused a little difficulty when we landed. For maneuvering, it was possible. However, as Chris already mentioned, there was a lot of flexing in the wings from spar stiffness. And then for landing, our nose wheel did collapse, but our test pilot did a really great job getting the plane back on the ground in one piece without a left main. We weren't able to accurately measure the RFP requirement, stopped at about 20 feet. Oh, and also, yeah, so like Josh said, this is our camera mount, and it kind of sheared off the bottom. Here are some of the pictures. The one on your top left is right after rotation. The one on the bottom is our normal approach and landing. And then on the right is our climb out. And here's a video we have. So the one on the right is the GoPro footage. That sounds a little bit off. Spoiler.
It's kind of.
Go on YouTube. Iluvatar first flight.
Okay, so we did have a bounce on the man. I'm not sure if you were able to see it, but we did have a bounce, and then it landed on the nose gear. So we were unable to measure some of the RFP requirements, and then following that, some redesign is required for the FTA and future iterations of the Sting, which would include spar stiffening, as Chris already mentioned, checking the main gear nuts so that it doesn't fly off after rotation, and redesigning the nose gear. In summary, we did successfully flight test, which was not mandatory. We followed our flight test plan as best we could, and then we completed a flight cycle. The FTA does require some redesign, however, future flight test is possible. And now I'll hand it off to Claire and Colostro for project management.
So here are labor hours for detail this semester. As you can see, the majority of our hours are in fact in manufacturing. So manufacturing just started about a month and a half ago. So considering it's 1 month and a half, that's quite a bit of hours because professional development is class time and research. And we'll break it down on the next slide. So labor accounting hours versus predicted hours. So predicted hours were provided by Professor Howland from fall 2014's section. So we were well above hours, and we're thinking that because we wanted everyone involved in the manufacturing process and the design, we felt it was important that everyone was in XFAB, or at least 2 people at a time during manufacturing. So that could also play as to why we had so many more hours. So breaking it down, like I said, manufacturing hours, just under 340 hours, and that was in a month and a half. So there's a lot of time and effort put into the manufacturing alone. And then next was professional development. So a total of just over 2,750 hours for the semester. Materials cost. So in AXFAB, or from the Department of, from the College of Engineering, there are lockers that have supplies from previous detail design groups, and so we were able to actually use some of those parts. But the parts that we weren't able to use, we actually had to purchase our own. So majority of our budget came from our carbon fiber tubing. So that was $776 in just the carbon tubing alone. So that was a significant part of our budget. And then our foam for the inside the wings and in the empennage, as well as the foam core for the fuselage mold, that was just over $200. And then our instrumentation for electronics was our ESC, and then our transmitter, as well as a switching regulator. So those were our more expensive items. But altogether, our budget, we stayed under budget. We had just under $1,800. Our budget was $2,000, so we did have some room there if we needed to purchase any other items. Materials obtained, like I said, were from the College of Engineering. In the lockers, we had carbon fiber cloth to make the layups, as well as the e-glass. And then we were originally supposed to have 3 servos from the lockers, but one of them wasn't working, so luckily we had enough budget to purchase another one. And then the motor, which was the Attorney ERAU-5S. And so with the combination of the materials obtained from College of Engineering and our budget, we would have gone over, because just these ones that we had from previous classes was just under $860. Conclusion recommendation. So the timeline, I had this up earlier as well, but we accomplished quite a bit in this semester, and it's been a lot of work. But like I said, we started manufacturing on October 15th, and we flew on the 24th. So just over a month, we had all that done. So that was an incredible accomplishment. Limitations, recommendations. So the manufacturing plan, we had that reviewed during the semester, but we felt that it would be more beneficial to have it earlier on in the semester, and then we could then look into the specifics of how things were going to go, because we should have done our wiring differently or our connections differently, and that's why our cost was so high for electronics, because we had to keep purchasing more and more of these quick disconnects that Josh Day had mentioned were not so quick for disconnecting, reconnecting. Aircraft component availability, there is a local hobby shop, but they are limited to what they have, and so it was difficult when we found out we needed a new component or something. We had to order it and try rush ship it. So they had just suggested to us that if we let them know ahead of time what we're going to need, they can actually make us a kit with all those supplies we need, and that would be really helpful. And then wind tunnel testing. Mark Jaworska had mentioned our wind tunnel data was erratic, and so that could have been resolved by if we retested, but the wind tunnel was not available to us. So that would have been helpful if we were able to incorporate time or availability to retest. Acknowledgements, we'd like to thank Dr. Traub, Michael Rosnick, our pilot, Mr. Patrick David, and Danny Clauser in AXFAB, Machine Shop. Then our panel members, Dr. Lanning, Mr. Kenny Young, Mr. Kyle Arcurio, Garrison Robertson, and Connor Warren. And then we'd also like to say a special thank you to Professor Halbig and Dr. Beck last semester. Thank you. And now we'll open up for any questions.
I'm going to ask you guys to introduce yourselves first, and then I'll introduce you. And then 2 questions each to start, and then if we have time, we have 15 minutes to start.
Well, I'm Kyle Arcurio. Lockheed Martin, Skunk and Palco in flight operations. Great job. It's a great feat that you accomplished. Design Build Fly is near and dear to my heart. Ours is still an X-Band, I think. Yes, okay. So yeah, great job. Great accomplishment. So for slide 183, in your data from the structural test, how you found out the strain gauges weren't working. Was that during the test that you found that out, or afterwards?
We found out during the test.
During the
Yes.
Okay.
But then it was difficult. We did reattach some of the strain gauges and actually took off some of the rosette strain gauges and re-soldered them. But since they were so tight together, it was difficult. We would suggest that in the future, or if it was possible to kind of, I don't know if it's possible to find the strain gauges that were, spaced out more, but it was very difficult, the tiny spaces for the strain gauges.
Okay. Good recommendation. Listen. Yeah. Let's see. Not necessarily a question, but on 218 with your kind of the stuff you did beforehand, moving control surfaces and whatnot, in the flight test where we call it system checkouts, and just to make sure everything works before you go and hit the rubber to the road. So good job on that. That's a good practice. There are some test teams out there that don't necessarily do that, and then they run into problems that drives up costs and everything. And just the last question, 223. Maybe she spoke wrong. The lower left corner, she said, "This is our normal approach on landing. Do you normally land without one move?" I'm done.
Alright, hello everyone, my name is Connor Warren. I'm a mechanical engineer right now. I've done CAD work, TD work, graduated as an aerospace from here, astrotrack though, so I'm a little lost right now. So you can probably expect some easier questions. So first off, this may not be the most intelligent question, but why an inverted detail?
Morgan, do you want to take that?
So the main driver behind that was our pusher propeller. We do have the camera on the front, and we didn't want the interference of the propeller on the front. So we put it on the back, but to ensure that the tail wasn't getting a lot of interference, we wanted to do something that would get it out and away from that. And then of course some of the other designs we looked at did incorporate a detail, so we went along with that.
Okay. Just seems to me like you might get a little more control authority if your tail was actually in the stream, but I'm on there. I don't know these things. Let's see. Also, just some quick presentation notes. Overall, very good presentation. I'll just work a little on the pacing because there are times where I'm just blinking and slides are still making it past. There are other times where I kind of felt like we're just going on. So just a quick note. I had another question. Slide 134. So I found the foam Young's modules, but where did the carbon layup and carbon tube forms come from?
Andy, did you want to take this? Oh, Peter, sorry.
So the carbon layup, those Young's modules, they actually came from testing with 0.34. And the foam, that was from testing as well. But in the tubes, the manufacturer actually didn't supply Young's modulus. So basically, we assumed it was made out of carbon. We made the assumption that it would be approximately the same of 0.34. So that's where that assumption came from.
Okay, was there, since you made that assumption, was there a factor of safety applied to that?
To the 0.34, no, there was not.
I just asked because I only saw one factor of safety, I think. And I was kind of wondering, okay, where are you guys going to apply it? I know you're going to apply it, but
Yeah. Yeah. Okay.
so, I guess you've already answered that. But where did you get the factor of safety? That's a good question. So,
Yeah.
Josh?
What's
Mark,
it?
do you want to take that?
Okay.
Come on, man.
The factor of safety was originally applied to our ultimate loads that we presented. So our ultimate loads already had that 1.25 factor of safety that he used in his ANSYS. So everything that he was calculating already had a 1.25 factor of safety built in.
okay, good. Just because I was a little confused about that. All right, thanks. Well done.
Hey everyone, my name is Garrett Robertson. I was the TA for the prelim last semester, and I was a member of the 2014 group, so I know their project decently. I would like to pick a bone pick with you because you said your hours were because you included everybody. But we included everybody too, so just throwing that out there. And then one thing I would like to see is what requirements you actually met and didn't meet. I think that was purposely left out of this presentation. So just because, all right, well, I'm fine. You guys had the 30-pound weight limit, right? Okay, so I just wanted to make sure that didn't change between the last 2 semesters. I did have a question for the STA, because you guys did have that massive deflection, and I mean, we had that too, so I was just kind of curious what you guys, if you observed anything that you could chalk that up to besides just ANSYS being different, so.
Welcome to the Peter.
So there were several things actually in the model that were predictable. First, first structure tested, we actually even have the foam support underneath it, and it was really bad then. We added that in first to help alleviate some of it. Then if you notice, if you look at the photo of the actual structural testing, there's a lot of deflection happening. There's a discontinuity in the curve it's deflecting right at that first disconnect point. And we believe that to be due to the ferrule not being sized large enough. And in addition, that there is some play in the tubes. They're not tolerance tight enough, or they're not epoxied in the right way. And that little few degrees of play, like half a degree of play that far on the wing, over the 7 foot per wingspan, that is multiplied into a very large deflection, and that was not accounted for at all in the ANSYS model. So that's another reason that the wings deflecting so much in the actual structural test.
Another large factor was we had I talked about a small tip profile, and so we just had to use really small diameter carbon fiber tubes. And the other team, they actually used larger tubes than us, and they saw less deflection because of it. So that was the main thing. It was just such a high aspect ratio wing, such a small airfoil, but such a small tip profile, and that led to small spars, which led to lots of displacement.
Yeah, we observed the same thing. If you go to slide 179, it's a picture of your test, and you can see where that joint is, and where it totally bends. We saw the exact same thing, so I'm just glad you guys actually caught that. So that's what we figured too, that degree of move, that amount of space you could wiggle in that big deflection. So my last question is, do you guys believe that your asset is ready to be, like, if you were selling to somebody, like trying to sell it to me, is it ready to go to be sold, or what else would you want to do before you'd be good to go for that?
Well, one thing we would do first is strengthen the nose gear, as you can see. Secondly, we would stiffen the wings and make sure all the control surfaces actually give us good authority and good pitch rates. And after that, we would consider selling it to someone.
Yeah, it feels good to fly though, huh? So, all right, good job, guys.
Excellent job, guys. My name is Kenny Young. I'm with the Boeing company down in Mesa. I like helicopters, and it's been a long time since I've been in your guys' shoes. Currently, I work in field engineering, but by trade, I'm a licensed engineer, so I'm pretty close to production fact. So 2 questions. Really? Jim?
To start.
All right. Let's go back to slide 70. Let's just go to slide 82. Looking at your guys' test coupon results, and even on slide 79, you tested 3 or 4 coupon testing. You guys have scatter everywhere. So my question is this statistically significant in how you determine your Young's modulus and Poisson's ratio?
What did Andy?
It definitely has a big effect, considering that they're not consistent at all. So our Poisson's ratio, sorry, can you repeat the question?
So looking at values on slide 82, all right, you guys list your 4 specimens in each result. And just looking at your E-glass, your first specimen gets right around 9,200 PSI, and then your specimen 4 is 2,300 PSI. That's a pretty significant range difference, and yet you still keep those in your average to say these are what our test panels are going to be. So how do you guys make that determination that your values can be used to size your model?
That was actually a mistake putting that in there. That should not have been an average. As I stated during my presentation, that model most likely failed in bearing load. So it didn't fail in the way that we wanted it to.
and that should not have been in the average. That is a mistake. Okay. So I mean, that's just something to consider. You have such a large spread, and when people look at published data, that's one of the things they're going to see. Do you have repeatability in your test results? Okay. Just one little observation that I did see when you guys listed your margin of safety equation. You guys said MOS. Unless it's changed, it's usually represented as MS. That's not a huge thing, it's just something I'm not typically used to seeing. Second question, going back on the structures fab side. When you guys sized up the thickness of your ribs, you came out to something around 3/1000ths of an inch. Have you guys looked at what 3/1000ths of an inch really looks like? With the micrometer? Yeah, does that number seem realistic in terms of a fab standpoint?
No, that's why I went with the 2 layers of carbon fiber averaging 0.025 inches.
Okay, so something just to keep in mind is when you guys start really sizing things up, Dr. Ashworth has this nice nomenclature of does that look right? Or does that seem right? Right? So let's take a step back and say 3/1000ths of an inch. On paper, that's what it says, but realistically, this is practical, this is real. So when they start looking at around the rest of the industry and saying, 3/1000ths of an inch, there's nothing that we can fab, even from composites, that's 3/1000ths of an inch. Especially when your starting point is 5/1000ths of an inch dry. So aside from that, very good aggressive schedule. I'm glad to see you guys put that goal for flight testing out there. It's nice to have a higher ceiling to shoot for. Break through your initial goal and then you hit your second. So excellent job.
Well, I'm Dr. Lanning. You have need for material. I'll look at a couple slides. I noticed some discrepancies. Slide 195. Okay, so you said the predicted wingtip deflection was 1.4 inches. Now slide 146. You have 0.31 inches at the wingtip. Is that answers? Are those the same?
That's a mistake. That should have been a mistake.
Which one's the mistake?
The 0.31. That was from an earlier iteration. That was from an earlier iteration at incorrect values.
Okay. Slide 134. We've got the Young's modulus 5.32 MSI. Slide 78. 61.6 MSI for E, which is the correct one there.
What was the previous slide?
134. If those are the same layout, there are 2 values there. One's an order of magnitude higher. I suspect that one's the more correct. 60 MSI is really high. Maybe you remember that in materials and the same thing. Should be MSI. I'm fairly certain around 5 to 6 MSI.
The 5 is the one where you measured it averaged out to be.
Okay. So we're checking what got used in ANSYS.
These, that 5.3 is the one that was used in ANSYS.
And someone double check all these things is certainly important. Slide 182. Slightly different here. So you've got axial strain gauges on the tubes there. You've got your ones on the rib, right? And if you go to the CAD model, it shows where the strain gauges are located. Where is that? Somewhere you've got the CAD model, and you show a pin through each of the tubes. Where is that? Yes. So those are pins that are holding on the, yes. Do you have those pins in the holes and the connections modeled on ANSYS? Is that part of the ANSYS?
The connectors are not part of the ANSYS model because it was we made the assumption, although it warrants now going back and checking it, we made the assumption that it was going to be fixed enough that just following the ferrules, considering the spar fixed to the ferrule was a good enough assumption at the time. However, after looking at structural test article, it warrants further reevaluation for that.
So your tubes are not continuous, of course. They chop off to the left or to the right of the pin?
To the left. The pins, because that's the ferrule connection. So there's a ferrule underneath that spar, which is what that red line represents. So that's basically the pin that connects the outer spar to the inner ferrule.
You got a lot going on there, and that's likely to affect strain gauge. You got a hole, and then of course no load is transferred from the hole. You got where the tube chops off, no load transfers through that, so that leaves some load. You've got the ferrule underneath there, and that perhaps stiffens the whole thing up. There may have been better places to place the strain gauges.
So the strain gauges were placed there due to the ability to access them in case something did happen when putting the spar into the wing and such. And then also the holes and the pins, the holes weren't drilled yet and the pins weren't in when we actually tested, due to the fact that if we put those in, we would have drilled through the wires, which would have ruined the strain gauges anyways. So that could, not having that pin there could also add to the amount of deflection that we did have in the wing, because when we tested it, we didn't have that pin there.
I suspect that might have been some of the cause of some of the difficulties. Last real quick thing, slide 56. So this is the lift distribution for your empennage. How did you decide to simplify it that way?
Chris, take this.
So, okay, what do you mean by simplify? Let's talk about how we get from what simplifying assumptions do we use?
Well, so if you go to the next slide, now you have shear load be zero at the side of the empennage when in fact it's actually connected to the boom, right?
So we assumed it was fixed at the angle rather than fixed at the boom, because this will give us higher loadings throughout. In reality, it'll be fixed at both ends, and so we'll have a zero somewhere in the middle. But we did this, is it'll give us a higher loading, and we'll get it's a more conservative estimate.
May or may not be true. I don't know that that will give you a higher loading for sure. I guess it could be, but it made something kind of unrealistic. Of course, you got shear weight treatment, and what you got going on right there where they're connected, it acts fixed to the moment, but not for shear there. So you got this continuity in your shear that's not realistic. And your moment, it shouldn't be there. It should be continuous at some point. So you've got something that's a fair amount different. You might have looked at the statics and then developed some sort of a shear diagram. Perhaps instead, there's probably another way to estimate it. Compare that to that, and then say what's conservative. So, I am done. Any other questions?
Time for one more quick one.
So you guys used SLS or your 3D printer to make your gimbal for your camera. And I noticed you guys fabbed up your nose cone out of an e-glass. Why not just use SLS to make your nose cone? Wouldn't that be a whole lot easier? I'm sorry, no one take that idea.
Well, one is the cost of the 3D printed material is pretty expensive. So, I mean, the cost between having to use some of our budget for that to being able to just use the e-glass that is already in the manufacturing lab was significant, as in we didn't have to spend any money for the e-glass, and we would have had to spend couple hundred for the 3D printed piece.
Couple hundred? Weren't you guys under budget? $200?
Hey.
I'm kidding. It was good though.
It's not hard. I was just curious. So when you guys were doing the wind tunnel testing, did you actually observe anything going on with the model to give you that weird data? And if you did, or if it just gave you bad data?
I will take it.
So originally our drag data, well, drag's supposed to be 0.0 something, 0.0345. Originally we observed it to be 0.5, 0.6, 0.7, and that was because the tear on the drag was about 0.5, 0.6, 0.7, since it had a giant balance sticking out into the free stream and caused a lot of drag. Once we subtracted that, we got those values, but the other team did get good smooth drag data when they retested, but they did have erratic drag data when they first tested. And I talked to Dr. Traub, and neither of us could figure out why it was so weird. They just tested one time it was erratic, they tested another time it was smooth. So,
Cool.
couldn't really answer that.
That sucks, I'm sorry.